Hello, so what we're going to have a look at is the Haber process. This is towards the end of C10, which is user resources, and this is higher tier only. Right, so in the Haber process is the production of ammonia. Now, ammonia is a compound that contains nitrogen and hydrogen. And ammonia is used for fertilizers, it's also used for dyes, it's also used for explosives. We'll have a look at how it's used for fertilizers in the main here. So, what we need to do is we need to put in the diatomic molecule that is nitrogen, so it travels in pairs, and that is a gas. We need to put in that diatomic molecule that is hydrogen, and again, it's a gas. And when they react together, it produces ammonia, which is also a gas, and the forwards reaction is exothermic, so heat is released. Okay, in terms of balancing the equation, I've balanced it for you. So it's N2, which is a gas, 3H2, so you need 3 lots, 3 moles, okay, to produce 2 moles of ammonia. Okay, the product that comes out in gas form, it liquefies once you cool it down, so you end up with liquid ammonia. Where does the nitrogen come from for this process? It comes from the air. Okay, so it's extracted from the air because the air is mainly nitrogen. Where does the hydrogen come from? That's extracted from natural gas. All of that is stuff that you need to know so far. So none of that is extra. All that is stuff that you need to know. Any of the nitrogen and hydrogen that doesn't react is refed back into the process to make ammonia again. I will point out it's a reversible reaction. Okay, so the forwards reaction is exothermic, the reverse reaction is endothermic. So once you reach dynamic equilibrium, you can have ammonia make these two as the products, or you can have these two reactants make that as the product. Okay, now the Haber process to make fertilizers involves an expensive industrial process. It involves a big unit. Okay, so the conditions are 450 degrees C in terms of the temperature, and 200 atmospheres of pressure. So if the atmosphere has 1 atmosphere of pressure, it's 200 times the value for the pressure that's needed, so 200. You also need an ion catalyst, and that is there so dynamic equilibrium is reached quicker. Remember, catalysts speed up the rate of reaction, and they also do not get used up. But because this is a reversible reaction, you would need to state that the catalyst is there to reach dynamic equilibrium quicker. So what do you need to know? You need to be familiar why we use conditions. So let's have a look at this graph and let's refer to Le Châtelier's principle from rates. So on the y-axis I've got the percentage yield of ammonia, and on the x-axis I've got the pressure used in atmospheres. And what I've ran is I've not ran it, have I? I've not done an industrial fertilizer experiment at home, but you know. What I've done is I've had a look at the 5 different temperatures. Okay, so 550, 500, 450, 400, 350. If we have a look at the conditions used, then we can see that our yield is there on our graph. Okay, now some of you will be thinking, okay, why don't we whack up the pressure to 400 and why don't we lower the pressure to 350? There are big reasons why, and I've just triggered myself because I haven't put a C on there. I apologise if I triggered anybody else. Right, if we look at Le Châtelier's principle, when we use a higher pressure, it favours the side with less moles. So high pressure favours the side with less moles. This is the side with less moles here, okay, because we've got 4 moles altogether there, and we've got 2 moles on the right. So if we use a higher pressure, it favours the side with less moles, therefore it shifts the equilibrium to the right. So high pressure, higher yield of ammonia. Also, it's worth pointing out that the forward reaction is exothermic because heat is released. Okay, so what we need to do to produce more of this, we need to decrease the temperature of the system. Decreasing the temperature of the system favours the side that's going to produce heat. So decreasing the temperature shifts the equilibrium to the right. Please have a look at the Le Châtelier's principle video again if you are uncertain. So why the compromise? If we whack up the pressure to 400, you're going to need a real thick steel unit. And it's very unsafe to operate at pressures that high, so that's why we don't bother. Okay, so pressure too high, we need a super thick vessel, more expensive, more safety regulations. Why don't we just decrease the temperature? It takes ages. If you lower it down to 350, it would take a lot longer and you have to pay more staff. It's not economically viable. So if we go for the temperature of 450, that is the compromise. Okay, so what you need to be aware of is all the stuff on this board here. Okay, so pause it, look through it, use GCSE Bite Size, use Physics and Maths Tutor, and then attempt some past paper questions. I hope this video was useful.